Students, today we are going to do an experiment on the cascade connection of two two-port networks. The two two-port networks that we will be considering are a T network and a pi network. All these resistances are of identical values of 1 kilo ohm each. We have designated it as R1 dash, R2 dash and R3 dash, R1 double dash, R2 double dash and R3 double dash. So let's start doing the experiment on the kit which has been provided. First of all, we connect the supply onto the milliammeter. The second end of the milliammeter goes to the T network and the second end of the source is going to the T network. Now we connect the voltmeter either to the supply and take the reading of V1 input, or we connect these two terminals here and we take the reading of V2. So let's start with the experiment. The voltage is increased gradually and you can see that since we are keeping the output open, it means I2 is 0. So A will be equal to V1 divided by V2. The voltage is increased gradually, and let us suppose we take the voltage supply to 11 volts, or we can make the milliampere ammeter reading to 5 milliampere, which corresponds to 11 volt. So note down, V1 is equal to V1A for the first network. V1A is equal to 11 volt. Current I1A is equal to 5 milliampere. And for V2A, we will shift this voltmeter onto the output terminal of the T network. So V2A gives you 5 volt. So V2A can be noted as 5 volt. First we are taking all the readings. Later on I'll show you how to calculate the values of the parameter. Next what we are going to do is step 2. The T network gets replaced by the pi network and the entire circuit remains as before. Okay? So connecting it back to the supply, and these two terminals are shifted from here to here, and you can see for the same voltage of 11 volt, the current has now become 15 milliampere. So we note down V1B as being equal to 11 volt and I1B is equal to 15 milliampere. Now in order to find out V2B, we take this terminal out from the supply and put it here at the output terminals. And we find that the voltage is somewhere in between 5 and 5.5. Removing the parallax error, it comes out almost to be 5. So we note down V2B as being equal to 5 volts. So we have completed the first two steps. Now let us move on to the third step. We interconnect the circuit in cascades. So the T network and the pi network are now connected. These two terminals, which were the output terminals of the first network, and these two terminals, which were the input port of the input terminals of the second network, they are connected. This is connected here, this is connected here. Okay, and the same circuit as before we make. These two terminals which were coming onto the T network, pi network, are now going onto the T network, and here we connect the output of T network to the input of pi network, and similarly the common terminals, and our cascade connection is over. Here you can check the voltmeter is right now in the output port. So the voltage that it is going to give us is 1 volt. We note down the voltage. Voltage is 1 volt. Which voltage? Output voltage. So we note down here 1 volt. What is the current? The current comes out to be, it's 2 small divisions ahead of 5, that is 6, because one small division is corresponding to 0.5. So here we note down 6 volt, 6 milliampere. Now we measure the value of voltage V1, the applied voltage. Take out the terminal from the output and connect it to the supply. And then we find the value of V1 to be 11 volt. So we note down 11 volt here. Now we move on to the fourth step. Let me explain you what is fourth step first. In the fourth step you find that the supply voltage is connected to the milliammeter, and then it goes to the T network just like before, and after the T network, instead of having a voltmeter here, now we are having a milliammeter. So basically the terminals of the output 2 they are getting shorted through the milliammeter. Now on the kit you can see there is only 1 milliammeter. So the milliammeter will be used twice. Once when you are using it in the input side, then the output terminal will be shorted by a direct wire, and when you are using here, then it will be, these two terminals will be connected directly. Okay, so now let's move on to step 4 and try to measure the values of V1A, the voltage here, supply voltage, I1A, the current, then minus I2A, the current which is flowing here. I will like to again repeat that the current which the milliammeter is reading is not I2A, it's minus I2A, because as per convention of two-port network, I2A always enters inside the network, and here the current which you are measuring is coming from this direction in this way. Here is the supply, the current division is taking place here, and the current is moving through this. So 1K and 1K basically are coming in parallel, and the parallel combination, that is half K, is coming in series with 1K. So overall, whatever is the voltage here, that divided by 1 plus half, that is 3 by 2, gives you the value of current I1. And this current is half of it, because a current division is taking place at this end, and these two resistors are of equal values. So now let's do the experiment, the step 4 of the experiment. In the meanwhile, I had disconnected all the terminals so that it's easier for you to perceive again. From the supply, we go on to the milliammeter. The second end of the milliammeter, goes to the T network, and the other terminal 1 dash, that is going on to the supply. You can in the meanwhile switch it off, decrease the value of the voltage to 0, and here we will short these two terminals. Shorting the terminals means the voltage has become 0. So this part of the experiment is when the output terminal voltage has been 0 and we are trying to measure the values of 1, the voltage across the supply, and second, the current after interchanging the position. Okay, so now let's switch on, gradually increase the voltage. Let's suppose we make it, okay, can we move on to maximum 12 volt? Okay, I'm changing the reading. We can have the same reading as well, but I'm changing it. Now the value of voltage you can see is 12 volt. Corresponding to the value of voltage 12 volt, the current which it is giving, I1, that is coming out to be 7.5 milliampere. 7.5 milliampere. Now in order to determine minus I2A, what we are going to do is, we are first of all going to switch off milliammeter ends, that is this one and this one. This milliammeter ends are now connected onto the output. Thus, two 2' terminal, which is denoted here by 6 and 8, they are being shorted on through the milliammeter. Okay, the supply has to be connected here. So get a wire and connect the supply. Connect the supply here. Switch on the supply and gradually you can see for 12 volt you are going to get the value of current as 4 milliamperes. So this current comes out to be 4 milliamperes. Note it down. In the next part, as you can see, in place of the T network, we have replaced it by the pi network. So these two terminals, I'm bringing from here onto here, and the rest of the circuit remains same. Then what current it is going to give? Right now the current which is being measured is on this side, so it is going to give you minus I2B. Remember, now it's going to give you minus I2B. So I just switch it off for a while, take out these two terminals and bring it here. Take out these two terminals and bring it here. So the entire network now has shifted from T to the pi. Switch on the circuit, take the readings. It's going to give you V1, B, which comes out to be 12 volt because we haven't changed the value of voltage. So it's same as before. And minus I2B because it's on the secondary side. Minus I2B, that is coming out to be 2 divisions ahead of 10, that is 11 milliamperes. Now we need to find out I1B. In order to find out I1B, this terminal which is directly going here will now come on to the milliammeter. Okay, so first switch off. This terminal which is coming here is now going to the milliammeter. So it goes to the milliammeter. Milliammeter second end is feeding the, is going to connect the terminals 1, 1 dash of the pi network. And these two terminals will now be replaced by a short circuit. Earlier it was sorted through the milliammeter. Now we have used the milliammeter in the circuit on the input side and we switch on the supply. You can see the value of voltage as before is 12 volt. And here the current you can find, it has gone up. It has become almost 22.5. It's above 22 and because of the least count we cannot be so precise. So you can take it as 22.5. So here we note down 22.5 milliampere as the current. 22.5. This completes our 5 steps. Now the last step. We are going to connect them in cascades. Okay. So now what you are going to do is first switch off as usual. You can decrease the voltage to 0. These two terminals which were connected from the supply on through the milliammeter onto the pi network now goes on to the T network. Clear? So just see, the supply is coming on to the milliammeter second end is going here to the T network, and T network second end is going on to the source. These two wires are for the measurement of voltage, so keep it aside. Now this is the point where we were shorting the other network. Okay, so this is shorted. Now these two terminals are to be connected and these two terminals are to be connected such that the output here becomes the input here. Are you getting it? So now we connect one wire here, red one, and as per our convention a black wire onto the grounded circuit, that is here. Now our connection is over. We'll switch it on and take the readings. You can confirm it with the diagram once again. See, the supply goes on to the milliammeter end goes on to the T network. After the T network, the ends of the T network are connected to the pi network. Here there is interconnection. Here there is interconnection. Here there is interconnection. These two wires are being shown here. This one and this one. This is the interconnection. Now you have the pi network, and after the pi network, either it can be shorted through a milliammeter or it can be shorted directly. Here we have shorted it directly and we are going to take the reading I1. So I1 will be equal to I1A for the first circuit. V1 will be equal to V1A for the first circuit, and let's take the values of those readings. Switch on the supply. Increase the value of voltage, and let's try to take the same value as we had taken while we were shorting for the 12 volt. Okay, let's make it as 12 volt. That's 12 volt. For 12 volt input, what is the value of current I1? You can read it here. It's 7, because between 5 and 10 you have 7.5. Just one division lower than that, that is 7 volt, 7 milliampere. So I1A we know 7 milliampere. Now we ought to find out what is the value of I2A. As usual, switch it off first. These two milliammeter ends, just see, you don't have to get confused. These two ends of milliammeter are being removed from here. Okay, are being removed from here. We keep it aside. Now the terminal which was connected onto the supply has to be connected back. So just get one more wire. Okay, let's take this one and connect it to the supply. So now we are having the supply connected directly here. These two terminals are out, and the shorted terminal wire, we take it out and connect these two terminals here. Our connection is complete. If someone might be feeling uneasy why sir has connected the black wire, I'm just making a red wire for the positive to be connected onto the network, because now we have that wire with us. Switch on the supply and you can see this is 12 volt. If it's not 12 volt, you can just increase it so that it becomes 12 volt. 12 volt, and here you can see the current. The current is 1, 2, 3 divisions. Yeah. 3 divisions, that is 1.5 million. And as told earlier, this 1.5 is not I2, this is minus I2. So this becomes 1.5 milliampere. Now that we have taken all the readings, I'll do the calculations after switching off the circuit and removing all the wires. Students, you are already aware of the transmission parameters equation. V1 and I1 are expressed in terms of V2 and minus of I2 in this way. So, A was equal to V1 over V2 when I2 is 0. C is equal to I1 over V2 when I2 is 0. B is V1 over minus I2 when V2 is 0. And D is I1 over minus I2 when V2 is 0. Since the voltage being measured in the experiment is in volt, the current being measured is in milliampere. So, volt divided by milliampere, the unit will always be equal to kilo ohm. Similarly, the current is in milliampere, this is in volt. So, whatever value you are going to get, the unit will be millimho. And these two ratios do not have any unit. Now, let's take the readings which we had and try to find out the values here. V1A is 11 volt, I1A is 5 milliampere, V2A is 5 volt. So, A is V1A over V2A. V1A 11 volt divided by V2A 5 volt. So 11 by 5, we find it out as 11 divided by 5 is equal to 2.2. CA, I1A divided by V2A. I1A is 5 milliampere, V2A is 5. So 5 by 5 is 1 millimho. Similarly, AB, V1B by V2B. V1B is 11, V2B is 5. So 11 by 5, same value as before, that is 2.2. And here you have CB as being equal to I1B by V2B. I1B is 15 milliampere, and this is V2B is 5. So 15 divided by 5, that is 3 millimho. Next we move on to step 3, where we are interconnected the networks and we find out the value of A. A comes out to be V1 by V2, 11 divided by 1, that is 11. And C is equal to I1, 6 milliampere divided by V2, that is 1 volt, that is 6 millimho. We come on to step 4. In step 4, we find that the value of BA is V1A over minus of I2A. V1A is 12, minus I2A is 4. So 12 divided by 4, that is 3 kilo ohm. And I1A over minus I2A, that is 7.5 divided by 4. That is going to give you 1.875. Similarly, coming on to BB is V1B 12 divided by minus of I2B 11. So 12 divided by 11 is equal to 1.091 kilo ohm. And similarly, I1B by minus I2B, that is 22.5 divided by 11. 22.5 divided by 11 is going to give you 2.045. Now the last step, after the interconnection and shorting, the value of B is V1 over minus I2. V1 is 12 divided by minus of I2 is 1.5, and the answer comes out to be 8 kilo ohm. This is perfect without any mistake. And D, which is equal to I1 over minus I2, that is 7 divided by minus I2, that is 1.5. So 7 divided by 1.5 is equal to 4.666. So it can be rounded off to 4.67. So now we are having all the values. Let us tabulate it and then check it out whether these values correspond to the theoretical ones or not. So we are tabulating the values. We can see AA 2.2, CA 1, AB 2.2 and CB 3. 2.2, 1, 2.2, 3. From the next part, BA 3 and DA 1.875. BA 3 and DA 1.875. Similarly, BB 1.091 and DB 2.045. BB 1.091, DB 2.045. Now overall, A 11, C 6 millimole, B 8 kilo ohm, and D 4.67. Now when we calculate using the individual ABCD parameter of the two networks, and by property, as you know, that T is equal to TA into TB taken in the same sequence, which we have done in theory. So the value that we obtain is 13.84, 8.53, 7.825, 4.925. And when you calculate AD minus BC, because the network is reciprocal, so reciprocity condition is being checked so that it's verified. Reciprocity condition is AD minus BC is equal to is coming out to be 1.41, and the value which it should give is 1. Now let's check up the theoretical verification. Since the ladder network is consisting of 3 rungs of ladder, 1, 2 and 3. So first of all, we are determining the T parameter of one rung of ladder. The direct values which has been told in the theory, 1 plus R1 over R2 here, R1 here, 1 over R2 here, and 1 here. Very easy to remember. 1 plus R1 over R2, R1 comes here, 1 over R2 comes here, and this 1 is coming here. Now R1 is 1K, R2 is 1K. Based on it, 1 plus 1 over 1, that is 2. And here 1000 ohm, which you can write it as 1K as well. Then 1 millimho, so you can write it as 1 into 10 raised to the minus 3, or you can write it for 1 millimho, and this is 1. Now 3 such networks are connected in cascade. So we are just multiplying these 3. On multiplication of these 2, you will get this. 2 2s are 4 plus 1 5, and then 2 1s are 2 plus 1 3. Similarly, 1 into 2 2 plus 1 into 1 3, and 1 into 1 1 plus 1 into 1 2. Multiplying again, 5 2s are 10 plus 3 13, 8 and 5. Compare these values with those obtained by multiplying the two matrices, and you will get the result to be very, very similar. 13.84, and theoretically it's coming out to be 13. 8.53, it's coming out to be 8. 7.825, it's coming out to be 8. And 4.925, it's coming out to be 5. So what is the inference that you draw after doing this experiment? The inference drawn is, for a big network, when there are many elements connected onto it, because of many inaccuracies in reading, etc., there can be a wide variation when you take the reading directly. See, 13.84 and 11, or 8.53 and 8, 7.825 and 6, 4.925 and 4.67, with regard to what it should come out to be. So here, if you don't get even AD minus BC near to 1. So it's always preferable that consider small sections, find out the transmission parameter of those networks and multiply those matrices. That is why ABCD parameters are very much used in transmission lines. In transmission lines, the whole transmission line can be constituted by various sections connected in cascade. By finding out the ABCD parameter of a small section of a line, you can go on multiplying on to it and you can obtain the relation between the sending end voltage and sending end current with respect to the receiving end voltage and receiving end current. Similarly, the second application of which will be asked to you in the Viva Voce exam, that how is it useful in analog electronic circuits or in amplifier circuits. Let us suppose we are taking a bootstrap Darlington circuit in which there are two transistors, common emitter transistors. So they are connected in cascade. The output of one is becoming the input of the other. And if one of them is having a voltage gain of 50, the other is also having a voltage gain of 50, overall voltage gain of the cascaded network becomes 50 into 50, that is 2500. 13.84, and theoretically it's coming out to be 13. 8.53, it's coming out to be 8. 7.825, it's coming out to be 8. And 4.925, it's coming out to be 5. So what is the inference that you draw after doing this experiment? The inference drawn is, for a big network, when there are many elements connected onto it, because of many inaccuracies in reading, etc., there can be a wide variation when you take the reading directly. See 13.84 and 11, or 8.53 and 8, 7.825 and 6, 4.925 and 4.67 with regard to what it should come out to be. So here if you don't get even AD minus BC near to 1. So it's always preferable that consider small sections, find out the transmission parameter of those networks and multiply those matrices. That is why ABCD parameters are very much used in transmission lines. In transmission lines, the whole transmission line can be constituted by various sections connected in cascade. By finding out the ABCD parameter of a small section of a line, you can go on multiplying on to it and you can obtain the relation between the sending end voltage and sending end current with respect to the receiving end voltage and receiving end current. Similarly, the second application of which will be asked to you in the Viva Voce exam, that how is it useful in analog electronic circuits or in amplifier circuits. Let us suppose we are taking a bootstrap Darlington circuit in which there are two transistors, common emitter transistors. So they are connected in cascade. The output of one is becoming the input of the other. And if one of them is having a voltage gain of 50, the other is also having a voltage gain of 50, overall voltage gain of the cascaded network becomes 50 into 50, that is 2500. Transmission parameters are thus useful in both power systems and in electronic circuits. Thank you so much.